In the previous video, we looked at secant lines and computing the average rate of change. I showed you a diagram that illustrated that as the change in x decreases, the slope of the secant gets closer to the slope of the tangent line. So as the secant line gets closer and becomes looking more and more like the tangent line, these dotted green lines get closer and closer to the tangent line. They do that when the change in x becomes smaller and smaller. So let's build on this intuition to show how to compute a derivative generally, and then we can use that general formula that we come up with in some examples. Now remember, we're trying to find the instantaneous rate of change. And to do that, we want to find the slope of the tangent line. Now, understanding the Newton quotient, which is also called the differential quotient, I want you to suppose that you want to find the instantaneous rate of change, which of course is what we want to do. And you want to find the instantaneous rate of change of f of x, specifically when x is equal to a, which is just some real number. In our example in the previous video, x was equal to 2. We wanted to find the slope of the tangent line when the function's coordinates were 2, 12. X equals 2, y equals 12. Now, in general terms, suppose we're looking to find the derivative when x is equal to a, or the instantaneous rate of change when x is equal to a. The point of tangency lies at what coordinates? Well, they're going to be at the coordinate a, because we want to know when x is equal to a. And what's the y coordinate associated with x equals a? Well, it's going to be f of a. Right? And so there are our coordinates. We're looking for the point of tangency, or the tangent line that just touches the curve at coordinates a, f of a. Now let's redefine our change in x. Common way to present the change in x is delta x, but let's redefine it as h, which is going to make reading our notation a little bit easier on our eyes. So h is going to be equal to the change in x. A secant crosses a function at the point of tangency. Remember, a secant is going to cross a function at 2 points. One of those points is the point of tangency. The other point is when what? How can we generalize the second coordinate where the secant crosses the function? Well, the x-coordinate, we're going to start with our initial point a, and we're going to add the change in x, h. Right? So if you had a is equal to, what is the y-coordinate? Well, it's just going to be the function computed at the x-coordinate. Right? So we might have a is equal to 2, like in our previous example. Let h be equal to 1, so the change in x is going to be equal to 1. That would give us what? That would give us the coordinates 3, f3. Oops. Yeah, that's right. Right? We would have 2 plus 1 gives us our x, and then the function at x, which is 3. Now we might want to combine all this. In fact, we do want to combine it so that we can get a general expression for the average rate of change. What's that combined expression going to look like? Well, it's going to be like delta y over delta x. So we've got the rise over the run, and that's going to look like, what's the change in y? Well, why don't we compute a value for y and then subtract, we can think of its starting value or its value at the tangent. And then we're going to divide this thing by what's the change in x? Well, that's easy. It's just h. And so there we go. This is our Newton quotient, or you might have seen it before even in this class, and it was called the differential quotient. And we're going to use this expression to find the instantaneous rate of change. So here we are on a slide. You can see the graph we've been working on with the secants in dotted lines, and they are getting closer and closer to the tangent line as the change in x becomes smaller and smaller. If we just want to know what the average rate of change of a secant is, we've got our formula right here. What is the average rate of change? It also happens to be equal to the slope, right? The rise over the run. Now the next step, the final step to finding the instantaneous rate of change, says let's let the change in x be very, very small, infinitesimally small. As h gets closer and closer to 0, as the change in x gets closer and closer to 0, the secant line gets closer and closer to the tangent line. How do we do that mathematically? Well, we can use the limit process. We can take the limit of the Newton quotient, or the differential quotient, and that will tell us what the instantaneous rate of change is, also known as the derivative. In this case, since we're starting with the function f of x, we're looking at the derivative of the function f of x at f prime a. And this little apostrophe up here, we verbally describe that as prime. So we say f prime a. For your information, in economics, we usually talk about the derivative. In engineering, it's more common to talk about the rate of change or the instantaneous rate of change. In economics, we usually just use the term derivative. But they mean the exact same thing.